All right, guys, today we are starting 9.8. And 9.8 is a bit of a doozy. It's one of the most important ones when we get into free response questions on the AP exam. We really see a lot that has to do with the power series, and more specifically, this idea of interval of convergence or radius of convergence. Now, we just got done learning about Taylor and Maclaurin polynomials. Now, these polynomials represent different functions. Okay, they were kind of like what we were saying, that like a tangent line, but a polynomial instead, which depending on how high the degree goes, the more accurate it is. Well, a power series would be an infinite polynomial, okay? An infinite polynomial, and then as you get to this infinite polynomial, it actually gives you the exact function that you're trying to represent. These power series are in the form of our infinite series that we've talked about, a sub n times x to the nth power. So they actually have an x, and when you start plugging in values for a sub n, you're going to get this long polynomial that's an infinite polynomial. Well, this would equal a function, okay? This particular power series is a power series centered at 0. All right, just like a tangent line has a point where it touches the graph. Well, where it's centered is where it's actually exactly the value of the function. An example would be like e to the x can be represented as a power function of this 1 plus x squared over 2 factorial plus x to the third 3 factorial until you get to x to the n over n factorial. If you were to add up all of the values when you plug in an x value, you would get the same value. This is an infinite series. And so what we can do is a power series can be used to represent non-algebraic functions. Okay. Now, wherever the center is, that's what I was saying, wherever the center is, that's where it's exactly the value of that function. Like when you plug in that number, you're going to get the same value as if you were to plug it into your function. Now, we can move the center left and right based on how we write our power series. And it all has to do with that x that was raised to a power. So if we have a sub n x minus c to the nth power, this would be centered at c. All right, centered at c, wherever it's moved left or right. Okay, that center really, just like we were talking about how, you know, the Taylor-Maclaurin polynomial approximates that value. Well, at that center, that's where it touches, that's where it's going to be exact. Okay, so this is an example of a power series. Okay, this is an example of a power series, and one of the things we talk about a lot with these is find the interval of convergence or find the radius of convergence. If you notice here, depending on what you put for x, this is going to converge. You know, right now, if I just leaving it like this, you know, x is a variable still. But if I plug in different values for x, then we can use our different tests that we learned in 1 through 6, whether it's going to converge or diverge. You know, if we plug in 1, okay, if you plug in 1 for x, right, it's going to converge. Right, geometric series test. Okay, if we plug in 6, for x, it's going to diverge. So for different values that you plug in for x, it could converge or diverge. And one of the big things we try to find, we try to figure out what interval of values will make this actually converge. And so if we take a look at this one, all right, from -3 to 3, this interval, all right, the power series would converge. Any value you pick between -3 and 3, this is going to give us a ratio less than 1, which using geometric series test would converge. And so this, again, becomes a really big component of what we're going to try and find with this. This is called, this -3 to 3 is called the interval of convergence. Of convergence. This is all the values that if you were to plug in for x, this particular power series would converge. Okay? And since this particular one is centered at 0, right? We think of that on a number line. Here's 0. We were just saying that it's -3 to 3. Well, this is your interval of convergence. Your radius of convergence is how far from the center you're actually going. So your radius of convergence is 3. Okay, so the radius of convergence is 3. Again, from the center, you're going 3 to the left, 3 to the right. All right, for the interval of convergence, so that gives us the radius of convergence. Okay, now this is going to get a little wordy, and I apologize. Anytime we do something new, it gets a little wordy here. But here's the thing: for a power series, centered at C, one of the following is true. Right, one, the series converges only at C, the center. Okay, so that's one possibility. The series will only converge at one particular value, which is at the center. In that particular case, the interval of convergence, which we're going to abbreviate with IOC, is x equals C. And the radius of convergence we're going to do with ROC is R equals 0. Okay, because it wouldn't converge on an interval, it would just be one value. That's one scenario. Our second scenario is that there exists a real number R greater than 0 such that the series converges or x absolute value of x minus C is less than R, and diverges where the absolute value of x minus c is greater than r. All right. This is our normal situation where we actually have an interval of convergence. And this will make more sense as we go through our examples, as we start working through this. In this particular case, our interval of convergence is actually going to be that interval. It's going to be c minus r, comma, c plus r. And our radius of convergence is going to be r equals some number. There's going to be a value actually associated with it. Okay. And our third scenario, all right, the other option is the series converges for all values of x. And when this happens, our interval of convergence is actually negative infinity to infinity. And our radius of convergence is r equals infinity. Okay, so these are really the three possible answers that we can get, or the three scenarios when we're looking for an interval of convergence or a radius of convergence. Either one, it's only going to work for one number and therefore there is no radius other than that one number. Okay, there's the possibility that you have an interval and the radius of convergence is some number, or the other possibility is it works for all numbers and therefore your interval of convergence is all real numbers and your radius is infinity. All right, well, we're going to be working on trying to find these intervals of convergences or radiuses of convergence. But first we got to figure out, hey, how do we find the center? So let's see if we can find the center on some of these. All right, state where power series is centered. All right, so looking at our first one here. The only thing you really need to look at is what is the x within the parentheses. Okay, if it's just x raised to a power of n, then the center is 0. But what we're looking for is this piece right here. All right, just like transformations, all right, transformations with functions and everything, when you have x minus 4 in there, it moves it 4 to the right. Well, our center for this one is going to be c equals 4. Okay, that's our center. All right, another one. And we have the series -1 to the n, x plus 5 to the nth power over n factorial. Again, all the extra stuff, not important. The only thing we're really looking at here is what's with the x raised to the nth power. And so we have x plus 5. Well, the center in this case is going to be c equals -5. Again, just like a transformation, a horizontal transformation left would be that. Okay. All right, so that's finding the center. The center is again going to be important for when we need to figure out where the radius is and how big the radius is. Let's go ahead and take a look at finding the radius of convergence. Find the radius of convergence. Our first example we're going to take a look at here is going to be the series n equals 0 to infinity 3 times x minus 2 to the n. Now, with all of what we're going to do, we learned the ratio test last out of our tests, right before root test. The ratio test is one of the most important ones we're going to use in this section because it gives us a rule for when something would converge. We knew the ratio test kind of over here on the side was if we take the limit as n goes to infinity of a sub n plus 1 over a sub n, it would converge if it was less than 1. And so that's actually the rule we're going to use for all of this. We're going to set up this ratio. We're going to take the limit as n goes to infinity of the absolute value of, we're going to take a sub n plus 1. Now this is not a fraction, so we're just going to do 3 times x minus 2 to the n plus 1 over a sub n, which is 3 times x minus 2 to the n. And we're going to make an inequality and say, okay, this is going to be less than 1. This will make it converge. Well, our whole purpose here is actually to solve for what x's make this work. We're actually going to solve an absolute value inequality, which I know it's been a while since we've done that, but it can be done. Okay, so first off, we're going to go ahead and simplify this. All right, so remember with simplifying here, we can cancel out the 3's. X minus 2 to the n plus 1 power is x minus 2 to the n times x minus 2 to the first. Well, that cancels out these, and it leaves us with limit as n goes to infinity of absolute value of x minus 2 is less than 1. Well, notice that we canceled out all the n's. So if we canceled out all the n's and you're taking a limit as n goes to infinity, well, there's nothing to plug infinity into anymore. So this is actually just going to be the absolute value of x minus 2 is less than 1. Again, that happens because there is no more n's left in our expression here. Well, now we're left with an inequality, okay, an absolute value inequality. And so when we solve an absolute value inequality, this is something we learn in Algebra 1, all right, we take x minus 2 less than 1, or x minus 2 is greater than negative 1. We flip the sign and change it to a negative. All right, and so this sets us up to solve x is going to be less than add 2 over, so 3, or x add 2 over greater than 1. So what this does here is it really sets us up for here's 1, here's 3, and then we have our interval, okay? We're not going to talk about intervals on this one. We're actually looking for the radius of convergence. We'll go back to the original problem. All right, we can see that our radius is based on the center. Well, the center is 2. So we see that from the center, here's our center, it's 1 to the right and 1 to the left. So our radius of convergence is going to be 1. Okay, so once you know where the center is, and once we've solved our inequalities, we can see that that radius of convergence is 1. Okay, let's try another one. All right, this one, n equals 0 to infinity, we have n factorial and x to the n. Okay, it looks a little different. Now, something to point out now, which I probably could have done in the beginning of the last one, what's the center? Okay, the center is 0. There's nothing added or subtracted to the x, and so since the center is 0, we kind of keep that in our mind when we find our interval. So here, let's use our ratio test again. All right, limit as n goes to infinity. All right, we're going to do a sub n plus 1, so that's going to be n plus 1 factorial x to the n plus 1 over n factorial x to the n. And it's going to be less than 1 because that's what tells us, the ratio test tells us is convergent. Okay, well, let's go ahead and start simplifying this. All right, n plus 1 factorial we know is going to be n plus 1 times n factorial. So we see the n factorials cancel. X to the n plus 1 will be x to the n times x to the first, which then the x to the n's cancel. And now we get limit, let's simplify this here. All right, we have an n plus 1 times an x. Well, the problem that we run into here, all right, what's that limit going to be? Well, we put infinity in there for n, we end up getting infinity, right? Last time I checked, infinity is not less than 1. This doesn't work. So when this happens, this is where your radius is actually 0. This is the case that we said first of those 3 possible cases where it only converges at the center. So if you were to think of this on a number line, the only spot that it's going to converge at is going to be the center, which is 0. So only converges at the center, because we got this untrue statement of infinity is less than 1. That doesn't work. All right, let's try a third example here. Can you guess if it's going to be the third scenario? Here we go. Our third one. All right, we have 0 to infinity, power series, -1 to the n, x to the 2n plus 1, and 2n plus 1 factorial. Okay, so we're going to find that ratio here. Or not ratio, yeah, we're going to use the ratio test. We're going to find that radius of convergence. Now, one of the big things about ratio test, there's a reason there is the absolute value. All right, we don't have to put the -1 to the nth power, because with the -1 to the nth power, that's the thing that's changing it from positive, negative, positive, negative. With the absolute values around it, we don't have to put that because it goes away. So what we're going to have here is x to the 2n plus 1 plus 1 over 2 times xn plus 1 plus 1 factorial. Ooh, that's a lot, right? And then we're going to multiply that by the reciprocal. We got a fraction here, so we're going to do this reciprocal. 2n plus 1 factorial over x to the 2n plus 1. And we're solving this for is less than 1. All right, lots to simplify here. So let's go ahead and start simplifying this down a little bit, make it a little bit easier here. We have limit as n goes to the infinity. This will actually be 2n plus 2 plus 1. So this is x to the 2n plus 3. Okay. And then from there, on the bottom is also going to be 2n plus 3 factorial times 2n plus 1 factorial over x to the 2n plus 1. Okay, well now we can start canceling some things out here and work through this a little bit. Okay, so first off, x to the 2n plus 3, right? That's actually x to the 2n times x to the third. Okay, x to the 2n plus 1, x to the 2n times x to the first. All right, that helps a little bit because now what we can do is actually cancel out the x to the 2n, x to the 2n, x cubed over x to the first. That's going to leave us with x squared, and that cancels out there. Okay, now what about the factorials? Okay, I know there's a 2n here, but think about what this does. 2n plus 3 would be 2n plus 3 times 2n, if I take away 1 plus 2, times 2n take away 1 plus 1, and it's going to keep going. Well, that's where your factorial is, and it's going to cancel out that factorial up there. So now let's write down what we have left here. We have limit as n goes to infinity of x squared's left on top, and on the bottom, the only thing left is 2n plus 3 times 2n plus 2. Everything else is canceled out. Well, let's evaluate that limit. You put infinity into the ends on the bottom, what happens is you get a number over a really, really, really big number. That's going to be 0 is less than 1. Well, that's a true statement. We don't have anything to solve with this, right? That's going to be a true statement. And so whenever that happens, our radius of convergence is infinity. That means it's all the values. Okay, so all values make this work. And make this series converge. Okay, if we were to put this on a number line, our center on this one, all right, was still 0. So actually all values made this work here. All right, covers the entire number line. Well, now let's switch gears and let's look at the interval of convergence. All right, still the same process. Because if you notice in that first one, we actually found an interval. We did find an interval in that first one. The challenge, though, is actually the endpoints. We got to figure out whether or not the endpoints are going to make it converge or diverge. And this is where all those tests that we learned in sections 1 through 6, or 2 through 6, come into play. We actually have to test those out. Okay, so let's start off with something relatively easy here. Okay, we're going to look at the power series x to the n over n. Okay, so we still start this out the exact same way. We're going to use the ratio test. So we're going to do our limit as n goes to infinity. All right, we're going to do x to the n plus 1 over n plus 1 times n over x to the n. Less than 1. All right, a little bit easier than the last one, huh? Now what we're going to do is go ahead and simplify. All right, we know x to the n plus 1 can become x to the n times x to the first. And that's going to cancel out our x to the n's, leaving us with limit as n goes to infinity of x times n over n plus 1. Now again, we're going for limit to infinity. Okay, so limit to infinity, this is where we still got to use that rule of insignificance. That plus 1 goes away, the n's cancel out, and what we're actually left with here is just the absolute value of x. Well, that actually gives us our interval. Okay, so once we get that, that sets us up to solve. So that means x is less than 1 or x is greater than -1. Okay, but here's the trick. We have an interval now. We know it's going to be between -1 and 1. Okay, but we got to figure out, what happens at 1 and -1. Okay, so we got to figure out, we have -1, we have 1, but now we have to check the endpoints. So once you get that interval, now what we actually have to do is figure out, okay, let's take x equals -1 and let's put it back into our original problem. All right, if we put it back into the x in our original problem, all right, we put that x in there, -1 to the n power over n, where n equals 1 and going to infinity. Well, what's that going to be? That's just going to be converges by alternating series test. Okay, so that means that at -1, we get a bracket. Okay, because -1 will make it converge, and we're trying to find all the values that make it converge. Let's try x equals +1. If we plug that in, we get 1 over n, or 1 to the nth power over n. Well, 1 to the n is always going to be 1. Okay, so we get 1 over n. Well, that diverges IP series test. And so if that diverges, that means we get a parenthesis around the 1 because that's not going to be included in the interval of convergence. And so if we were to put that on a number line, all the values that work here, our center was 0, here's -1, here's 1. It doesn't work at 1, it does work at -1, and it's all the values in between there on the number line. Okay, so we can see that here's the interval of convergence. Our radius of convergence, if we wanted, would have been 1, but we wanted the interval of the convergence on this one, which gave us -1 to 1, bracket, then parenthesis. Okay. If we were to find out, again, this is just kind of recap the other scenarios. If you have a radius of r equals 0, okay, then the interval of convergence is C, whatever the center is. And if you find out that your radius of convergence is infinity, then your interval is automatically -infinity to infinity. Okay, so this is 9.8, finding the interval of convergence and the radius of convergence. And I know it seems like a lot right now, and you're like, this is weird, and it's going to make sense as we continue to go through this last couple sections. This is a big part of what the AP exam looks for when we get to FRQs, finding that radius of convergence and interval of convergence, because not only do you have to be able to find that using the ratio test, then you have to use other tests to find the endpoints. And so we're going to spend a lot of time looking at that. But to next class, I'll go ahead and go over some questions on this, and we'll actually be taking a look at some other things going along with 9.8 tomorrow. Okay, so work through the assignment, try to go through that, use the solutions manual if you need to, and we will pick up on this next class. Good luck.